Assalamu alaikum and good afternoon for all. This is Assist Prof. Dr. Makram Abdul Muttalib Fakhri from University of Technology, Head of Branch of Optoelectronic Engineering at Laser and Optoelectronic Engineering Department. Welcome for you all, attendance and our audience, with the activity of the third International Conference on Material Engineering and Science that will be held at Kuala Lumpur and managed from Al-Nahrain University in Baghdad. Dear participant, it is an important note. Please prepare your presentation for 10 minutes and 5 minutes for questions. And the presentation should be in English, please. We can start now with the first participation, Mr. Ihsan Al-Permani, University of Babylon. Participation title, Influence of the Polymer Molecular Weight on the Electrical Properties of polyvinyl alcohol, polyethanol, glycols, graphene oxide, nanocomposite. Mr. Hassan.
Hi, thank you very much. I am Prof. Hassan Al-Permani. Yeah, I try to share. Yeah, okay. Dear all organizers and participants in this conference, thank you very much to allow us to present our presentation. So my presentation is the influence of the polymer material weight on the electrical properties of polyvinyl alcohol, polyethylene glycol, the graphene oxide, nanocomposite. I am Prof. Dr. Hassan Al-Permani from University of Babylon. That work is like shared with the Al-Mustaqbal University and Babylon University. So I will start my presentation with the contents that divided for these parts as presented in this slide. So the next slide with the introductions. You know, all the polymers is very interesting material, commercial, and used in different ways and method application. But these properties of the polymer, they have sometimes is like lakes in some applications, specifically like electrical properties and mechanical properties. So the nanotechnology comes to solve and overcome these problems. Then we can basically use a nanofiller. One of the best nanofiller used these days is the graphene, because the unique properties they have, specifically mechanical and electrical properties, even other properties like optical. So graphene oxide that I prepared in the University of Sheffield, I prepared it. It has like specific and unique structure, and they have like unique properties specific in electrical. That's discovered in 2014, and they get Nobel Prize by a member, also a PhD student in the University of Sheffield in 2010 to discover and separate this material from graphite. Graphene and graphene oxide is like derivative both of graphite, and this material they have a functional group that helps to contact with other material. Graphene involved in many applications. Engineering, they use this material in like cars, automotive application, like medical and other. It's like a variety and wide application actually. So the objective of this study is to prepare these materials by using like PVA and BGS with different material weights, and main object, the effect of like this molecular weight on the properties of the electrical properties. The second, when like use the graphene oxide as nanomaterial to enhance these properties, and of focus about these two factors in this investigation. So the experimental was the table on the left side show us like the ratio that used. So we used like a fixed ratio, the BPA about like 70% and 24% from VEG, then the GO is like 1%. We can see from the sample ID, the change here was we have like two samples, 4K and 4K with the GO, then 8K with the GO and 20K with 20K with GO. This material actually is very interesting because they has a lot of application PVA and VEG, even the graphene oxide. So we use like a VEG under 20K. The second graph on the left, on the right side, sorry, they have two steps. As we mentioned before, the graphene oxide was prepared in the University of Sheffield by me, and we use the Hammer method, is the famous method to prepare the graphene oxide from graphite with a chemical method, and then we use these steps just to prepare the the nanocomposites. So the characterization, we characterize the FTIR for the structure and optical properties, optical microscopy for like taking the image for material, then the electrical properties we focus about the AC here specific. The FTIR show us for this material, just we compare it first with the ethane polymer, then with the graphene oxide. Sorry. So we can see most functional group of both material, blended polymer and GO, these representing an all functional group. We can see that this functional group is like similar with small change in the intensity, or sometimes is like little bit shifting in the peaks. This confirms the preparation of a graphene oxide and also the successful preparation and as connecting between this material as a physical connection. There is no chemical interaction or connection or bonding represented in your hair. So the optical image on the right side show us like how this material involved in the graphene in this image for like a nanocomposite. The image is similar for the blended polymer. No big difference, so we choose just one. So that one is the 20K, and then we involve like the graphene oxide with 4G. We can see here the difference between 4G and 8, then 20K. 4K, 8K, and 4K. This when we use the graphene oxide with this material. The dispersion of the graphene oxide here is fine and is become better when we increase the molecular weight, specific in the last image is we will call this T. So the electrical properties, the AC, you can see from the AC with the frequency, the curve was increased firstly with the increasing, and we have get like the higher value at the frequency about 3 million. Then we move to the electrical constant. We can see both figures. The polymers blended, they have like a good properties, but it is improved when we increase the molecular weight, basically in both the AC and the dielectric. Also, the graphene oxide improve both properties like the AC works increase and the dielectric constant also works. So the molecular weight have like a significant effect as well as the graphene oxide. If we compare this material with the original material, with the blended polymer without GO, even if we compare the polymers with the molecular weight. So we have these two factors here. Also, the dielectric flues, we can see this effect is clear, and we make the last figure on the right side just to compare the AC electrical properties with time this with the molecular weight. With the increase in the molecular weight, we can see the blended polymer, the AC was increased. Even when we use graphene oxide, there is like a too big difference between these value. The nanocomposite have, the graphene oxide, he have like a strong effective even with an increase in the mercury. So these basically materials together, they get a significant and important properties, and also they have impact on the materials. So, increase the mercury as a conclusion from this investigation, increasing the mercury of PEG in the nanomaterials represented a significant improvement, especially specific. The high molecular weight, it has like better properties. That investigation shows us the molecular weight has impact on the properties of the polymer. Also, the contribution of the GO show us like improvement when we compare the blended polymer without GO with the blended polymer after adding the graphene oxide. So basically, this study focus on two parts. These two parts presented from this investigation is so important to affect on their properties. Thank you very much. I hope if you have the presentation is clear, and if you have any question, I will happy and try to answer this question. Thank you very much, Dr. Makram.
Thank you, Prof, for your presentation and for your timing. We turn now to the questions. Anyone has a question for presenter, please?
Any question, I will be happy, very happy to answer any question or any query. Something is not understandable from my presentation. Also, I will be happy to present it to you.
Anyone have any question? Okay, Doctor. Prof, you present dielectric loss for your work.
Yeah.
And I want to ask you test it or you measure it by from optical properties? This losses.
Yeah, actually, it is calculated. Yeah, it's calculated from equations. Yeah.
Yes,
it's not like measured directly from the device. You will
calculate.
Yes. Right.
You can use this composite for medical or for biosensors.
Yeah, actually, we have like another study focus about this material to use it in like a medical application, because PEG with the low molecular weight is very interesting in this area, as well as in sensor application, specific with the graphene oxide or the graphene. Thank you very much.
Very good. We can dope this composite with any other materials like lithium niobate or any photonic materials.
Yeah, actually, we focus about this area. Presently, this is very important to us to discover this area and application with like electrical device. So because that we try to use like different molecular weight to see how that will affect on the electrical voltage. It's better to use like higher molecular weight or low molecular weight. And like molecular weight is very important like factor in some applications, specific in like medical application. We normally use like lower than 1000 K or 1K for application like this. So it is possible, and we will try to do that. Thank you very much.
Thank you, Prof, for your presentation and your answer and your time. We turn now
Thank
to
you for your tour also.
Thank you very much. We turn now to the second presentation. Mrs. Fatima Hamid Malik, Polymer Research Center, University of Basra. The presentation titled Preparation and Characterization of CH over PBA over ZNO FA nanocomposite. Mrs. Fatima, please.
السلام عليكم دكتور.
السلام ورحمة الله. You can recognize yourself and start your presentation.
Yes. My Fatma Hamid Malik in Polymer Research Center, University of Basra.
Okay, you can start now.
My paper, interpretation and characterization of ketosane polyvinyl chloride, zinc oxide, folic acid nanocomposite. The polymer ketosane and polyvinyl chloride polymeride added to ZNO nanoparticle and folic acid with direct application. The sample characterization use FTIR, UV, spectroscopy, DSC, and X-ray with EDX. Polymer PVA and ZNO was in sigma aldrich, and FTIR by spectroscopy. Ketosane extraction by induction shape. Barbaric hydroxyl polymer and start ketosane chemistry barbar polymer in general, meaning from many points.
دكتور مكرم. دكتور الصوت ماكو.
نعم.
دكتورة فاطمة لا تسمعينا؟
أعتقد انقطع الإنترنت.
دكتور انفصلت من
ممكن ننتظر دقيقة واحدة وإذا هذا يحول على البرزنتيشن الآخر.
دكتور فصل النت اتصلت بي وما عليه كهرباء.
نعم.
ما يوجد الانترنت لديها.
ماشي. Then we turn now to the third presenter, Mr. Hussein Ala Bar, Material Engineering Department, University of Technology Baghdad. Presentation title: Investigation of fluorescent lamp glass used as a fluxing agent in porcelain pots. Dr. Hussein, you can present now, or you can recognize yourself and present. please.
Assalamu alaikum jami'an. Good afternoon. I will present my paper now.
Yes, you can present now, please.
Okay, you can see my paper, my presentation.
Yes, it's clear now.
Okay. Hi everybody. My name is Dr. Hussein Ala Jabir. I am head of Materials Engineering Department at the University of Technology. My paper name is investigation of fluorescent lamp glass waste as fluxing agent in porcelain bodies. The outline of this paper contains summary, objective, experimental work, result and discussion, and conclusion. The summary, fluorescent lamp glass waste, FLGW, has been used as a fluxing agent for preparing porcelain bodies. 3 different standard mixtures of porcelain bodies were prepared, which composed of kaolin, flint, and potash feldspar. The FLGW is added to the porcelain samples at different ratios, ranging of 0, 5, and 10 weight% as a partial replacement of potash feldspar. Centering behavior, physical, and mechanical properties of prepared porcelain was being measured. The objective of this research is include investigation the possibility of using waste glass from end-of-life fluorescent lamps as fluxing agent materials in porcelain bodies. And the second one, studying the centering behavior, physical and mechanical properties of porcelain product after added the FLGW. And third one, using the using of FLGW as a partial replacement of feldspar will help to reduce the cost of common porcelain products. And the last one, using of waste material as a replacement compound for production of ceramic bodies generally would help to keep on the natural sources in the world. Experimental work. The raw materials used in this work were kaolin clay and flint. This material is supplied from the Iraqi Geological Survey, and the potash feldspar, which was supplied by Winger Company, the UK. And the last one is the fluorescent lamp glass waste is produced from the commercial market. The chemical composition of these materials as shown in the table below. These raw materials were milled firstly and then saved to obtain the particle size about 19 micrometer for kaolin and flint materials, and while the feldspar and FLGW fluorescent lamps were crushed and then milled to obtain about 53 micrometer particle size. 3 standard porcelain mixtures have been prepared. It's coded as I1, I2, I3, as shown in this table. I1, I2, I3. The chemical composition is composed. The kaolin percentage was fixed for all mixed batch, while flint and feldspar will be varied. Feldspar will be varied from 13, 35, 14. The first group A, was composed without FLGW. And then the FLGW was added at different percentage, 5 and 10 weight% as a partial replacement of feldspar content. 5 in the group B, and group C 10 weight percent. From this percent was added was reduced from the feldspar content. The specimens were prepared by semi-drying pressing method. The water contained about 10 weight percent. The pressing process was done by a hydraulic press using mold made from stainless steel, have a diameter 13 millimeter, with the pressing pressure about 25 megapascal. The centric process was then carried out at various temperatures, about 7 temperatures ranged from 925 to up to 1215 degrees Celsius, with 10 degrees per minute at a heating rate and 1 hour soaking time. This is just the sample of the sample after the centering. Sample test. The first one is the bulk density and the apparent porosity was measured from the Archimedes method, and the thermal conductivity was calculated by the hot disk method, and then fracture strength was calculated by the diametrical conversion disk test as the equation 1 below, and finally the microstructure and characterization by XRD and SEM was measured. Result and discussion. Firstly, the bulk density of the apparent of the porcelain specimen. The bulk density increased with increasing the centering temperature, as shown in this figure, figure 1A, increased up to 1,225, and then the decrease. This increasing because due to the increase the contact between particles. The addition of FLGW to the porcelain bodies for specimen code B and code C work to reduce the centering temperature of porcelain specimen. The maximum density was about 1,000 for when added 5 weight percent, and reached to 915 when added 10 weight percent of FLGW. The apparent porosity of porcelain by the specimen is inversely proportion by from the density measurement. From the mixed code A, the minimum porosity was at when heating the centering at 1,225, and while when added 5% of FLGW was at 1,000, while when added 10% weight percent of FLGW, the lower apparent porosity was at 1,100 centigrade centering. The result of the thermal conductivity of porcelain specimen. This property was measured according for the samples which have higher bulk density values. So for the mixed code A, this part we measured for the 3 composed of I1, I2, I3, which centered at 1,225, as shown in this figure. With increasing the potash feldspar, the thermal conductivity will increase because this is due to the reduce the porosity. While with adding FLGW, as shown in this mixed code B and mixed code C, the thermal conductivity will be reduced. This is due to the lower thermal conductivity of FLGW with the increased closed pores in these samples. Fracture strength of porcelain specimen as shown in this figure below for mixed code A without addition, and B and C with addition of FLGW as shown. This figure is parallel with the density measurements. The microstructure characterization of these samples, as shown in this figure. For figure A, this figure for the samples without addition, it's as shown. It is composed of mainly of monite phase with crustoblite. With addition 5% of FLGW, it's shown that we can get higher peaks and sharp peaks at this addition. While with addition, when increasing the FLGW up to 10%, we can get more rough and lower peak intensity. The microstructure characterization also, as shown in the SCM, this is the fracture surface of the sample of specimen of A3. As shown, it's composed of some closed pores, while with addition 5%, it's composed of more compact specimen. With increased addition of FLGW, we can clear the fracture surface is composed of many of closed pores in this structure. Conclusion: increasing of feldspar content in porcelain bodies patch enhances the densities and fracture strength of porcelain. The maximum density and fracture strength values were obtained for porcelain patch composed of 14 weight% of kaolin, 20 weight% silica, and 14 weight% of feldspar. That started at 1,225. Addition of FLGW as partial replacement of potash feldspar in porcelain patch has a beneficial effect on lowering the centering temperature of porcelain bodies. The physical and mechanical properties of porcelain bodies reduce when added of high amount of FLGW up to 10 weight%. Thank you for your attention, and thank you very much.
Thank you, Dr. Hussein, for your presentation and for your timing. We turn now to the questions. Anyone have any question for Dr. Hussein, please? Okay, Dr. Hussein, can you please explain the application of this composite, please, and the economic and scientific feasibility, please?
Okay, the application of this material can be used as refractory materials and can be used as insulating materials. And this research can be replace the potash feldspar, because the potash feldspar is very expensive materials, and can replace part of these materials with waste materials, like as glass waste. This subject can be benefit for keep the source in the world.
Okay, then we can use an electronic component like MOSFET.
Yeah.
We can prepare
it can
a MOSFET.
Be porcelain insulator, like electrical insulator, heating insulator can be used. These materials.
Okay, thank you very much for your time.
Thank you very much.
We turn now to the fourth presenter, Mr. Firas Faiq, Al-Muthanna University College of Science, Department of Physics. The presentation title, Modeling of Mach-Zehnder Modulator using Ferroelectric Materials at 1.55 Joule Optical Transmissions. Yes, Mr. Firas, you can start now
Thank
and
you.
present your work.
Thank you, Dr. Makram. Assalamu alaikum. It's an honor to me for participating the third conference on material engineering and science. I think that's my second participation. I participated last year for the second conference, and I'm happy to join you in the third conference. Firstly, I would like to thank you, Dr. Makram and Mr. Mohammed, for your great job, for your help. And secondly, I would like to thank my postgraduate student, Hanan Jassim, and co-supervisor, Dr. Muwaffaq Fadel Jaddour. My presentation titled Modeling of Mach-Zehnder Modulator using Ferroelectric Materials at 1.55 micrometer optical transmission. Optical fiber have received much attention in the last few decades because of their admirable properties like tiny weight, resistance to external electromagnetic interaction, and multiplexing capabilities, which offer significant applications like optical communications technologies and sensors. Optical fiber modulators play a major part for waveguides and integrated photonics applications, which operate with very small derived voltage due to its low size compared to the bulky counterparts. High modulation efficiency, good linearity, wide broadband. Mach-Zehnder modulator is one of the most important optical fiber modulators. In general, the Mach-Zehnder modulator is an essential element in the optical telecommunication networks, such as optical switching modulators. The light, the definition of Mach-Zehnder modulator, the light is pumped into the Mach-Zehnder modulator through port 1, then which is work as 50 by 50 coupler. So the power is divided in equal rate and launched separately into the directional coupling section. Finally, the two transferred waves are recombined and can take as an output by port 2 or 3. The modulation effect in Mach-Zehnder is obtained when the effective index in the optical fiber material of one arm is changed due to the applied and external voltage on it. Thus, the light phase for the propagate wave in that arm is modified. Numerical simulation and materials. Modulating of transferred light signal in optical system is achieved by applying an external electric field to change the concentration of optical carriers that lead to modify the index of refractive of the material. Phase modulation is realized by setting the suitable dimensions of Mach-Zehnder modulator structure. In this work, waveguide parameters that applied in this simulation were width is 2 micrometers, total waveguide width 30 micrometers, and coupling length is 300 micrometers. The frequency of the incident electric field was set to be C over lambda, where C is the speed of light in vacuum, and lambda is the wavelength, which is equal to 1.55 micrometers. The analysis of Mach-Zehnder modulator design is made by using COMSOL multiphysics software and finite element method, FEM. Based on the above Mach-Zehnder modulator parameters, finite element method is mathematical method to solve Maxwell equation for electric and magnetic field. the most general mathematical model describing electromagnetic fields and their dynamic interaction with media is given by Maxwell equations as shown below. Three kinds of ferroelectric materials have been used in our simulation, which are lithium niobate crystal is a ferroelectric material that widely applied in the nonlinear optics applications and optoelectronic, utilizing its large nonlinear optical and electro-optical coefficients. Tritium titanium is the perovskite type crystal widely used in optoelectronics and electronic systems as a result of its high dielectric constant, about 300 at room temperature, that highly changes with the electric field. Potassium nitrate is a ferroelectric material, has spontaneous polarization even with electric field, and their polarization state can be changed under the effect of the external electric field. Table 1 describe the refractive index and chemical form for three types of material that used in our work. Firstly, the lithium niobate material with N core, refractive index of the core equal 2.22, and the refractive index for clad equal 2.2, and the other materials, tritium titanium, the refractive index of the core equal 2.3, and the clad refractive index 2.28, and third material, potassium niobate, the refractive index of the core equal 2.12, and the clad refractive index equal 2.1. Results and discussion. First, we discuss the power difference and coupling length for every material, for the three materials. We find from these figures that the coupling length of, firstly, the transmission light make the coupling 50-50 between two ports, and this is success the Mach-Zehnder modulator. Then we can find that for three materials, the coupling length is different from one material to other, where the minimum coupling length we get from the material of the lithium niobate material. Second results, the total transmission and band radius. According to the result shown above, we can find that for the three materials, we have a transmission and band radius. The three materials are the same, around the same values, and this is according to the physical and optical properties of these three materials. The first figure for the Mach-Zehnder, for the electric field for the base lithium niobate material with the total model transmission, and for the second figure for the tritium titanium material, and the third for the potassium niobate material. Third result that we find and we calculate the transmission and the applied voltage. For three materials, we discuss or we calculate the transmission when we and get the applied voltage for the input port and output port, and we can find that for the three materials we have coupling in the lithium niobate, and for the second material tritium titanium and potassium niobate, we can find the coupling length, and this is according to the applied voltage and cause the applied voltage to be reduced. Conclusion. Theoretical and simulation study of the Mach-Zehnder modulator based ferroelectric materials by using finite element method is achieved. Results showed that the lowest coupling length of Mach-Zehnder modulator was 304 micrometers by using potassium niobate crystal. Mach-Zehnder modulator is operate as a modulator at band radius of curvature with 2.5 millimeters. For all ferroelectric crystals, for three ferroelectric crystals that used, and Mach-Zehnder modulator didn't work with lower than 2.5 millimeter than this radius. The effect of applied voltage showed that the Mach-Zehnder modulator is operate actively and effectively at 0.38 voltage by using tritium titanium material, and this is the best one for choosing the applied voltage in this work. I would like finally, I would like again Dr. Makram and Mr. Mohammed and my partners, Dr. Muwaffaq and Hanan, for their great job, and I'm ready for any question. Thank you again.
Thank you, Doctor, and for your time and for your presentation. You have very interesting work, and we can turn on now to the questions. Anyone of audience have any question, please? Yes, Dr. Roma? Yes, Dr. Roma, you can ask now. Okay, I can ask you some question now.
Of course.
Dr. Muwaffaq, you have a very interesting work, and your work modeling by using COMSOL program.
Yes, yes. I'm Faraz. I'm Dr. Faraz. My partner, Dr. Muwaffaq.
Yes. Okay.
Thank you.
Dr. Faraz. Anyway, you try using you now using a crystal, lithium niobate crystal, and other crystals.
Yes.
You try for using nanostructure for lithium niobate or other materials like nanothin film.
Okay. Well, I think in our work in the for optical communication systems, we need to use nano rods systems and nano rods crystals because of their properties that match with the transmission of optical communication devices. As you know, we use this Mach-Zehnder modulator on other optical devices for the transmission of the future the future transmission devices. We can replace the optical devices by electrical devices. So we need to make the devices more compact and the speed of the signal more speedily. Then we need to use nano structures and nano rods for this applications.
Yes, correct.
Excuse
yes,
me. Excuse me. I am Luma Zuhair, a PhD student in laser department. Can you ask Dr. Firas?
Sure.
You use the refractive index for lithium niobate.
Yes.
For core and clad the same. How can you do this?
No, of course not. Firstly, I'm pleasure to hear Dr. Luma. Luma is my partner when we in the baccalaureate in the PSC study I think in 20 years ago. This is a good chance to meet her. Firstly,
nice to meet you.
Thank you. Dear Dr. Luma, we used different refractive indices, as you see in this slide. Anchor 2.22 and any class for the lithium niobate 2.2.
I want to inform you how you can use clad and core the same material. That
Okay,
can't
okay.
use it.
Thank you. The same material by doping. It's the same material as a chemical sample, but the doping is difference between the clad and the core. So you can't see the core material with refractive index different from the clad refractive index. This is because the the doping different. The difference in doping for the same material make the clad differ from the core. I mean, okay.
No, I think you use the ordinary and the extraordinary for lithium niobate. Yes.
Our study for this material and for literature review, we can find the degree of doping, and maybe we use the ordinary. Okay, no problem. But I think we can't apply something with the doping of material and make this different in refractive index.
Okay, thank you. I hope to contact you and discuss this.
Of course, anytime.
Okay.
Thank you.
Okay, thank you. Thank you, Dr. Makram.
You are welcome, Dr. Rama. Anyone have any question? Okay, Dr. Firas, thank you for your time.
Thank you.
Nice presentation.
Thank you, Dr. Makram. Thank you again for your great job. Thank you.
We turn now to the fifth presentation. Dr. Mohammed Hussein Al-Mishhadani, Al-Nahrain University Chemistry Department. Presentation title, Environmental and Morphological Behavior of polystyrene film containing shift base mainly. Dr. Mohammed, you can present now or recognize yourself and present now.
Okay, Assalamu alaikum everyone. First of all, I would like to thank all of you, and especially the organizers, and special thanks for you, Dr. Makram, and for Dr. Mohammed for a great job you're doing. I am Dr. Mohammed Hussein, a lecturer at Al-Nahrain University. And actually I'm here to present our work. It's actually my work and my colleagues, Dr. Imad and others co-authors. The title of my work is Environmental and Morphological Behavior of Polystyrene Films Containing Shift-Based Moiety. Actually, before I go to the next slide, just I'd like to highlight one thing, that the main aim of our work is reduce the consumption of plastic materials, especially the polystyrene. And you know the big environmental problem with the plastic, especially for marine ecosystem. So this is the main aim, is to synthesize new photostabilizers, so we will have like polystyrene or PVC and other polymers for longer time, and this will reduce the consumption of these important polymers. The outlines. First, I'll talk about the synthesis of shift base. Okay, maybe I need to press F5. Okay. So first, I'll talk about the synthesis of the shift base, which we name it compound 3. Then we'll do some study by using the FTIR spectroscopy to check the photodegradation of the polystyrene. Then we'll examine the weight loss of the polystyrene. Then we'll use some techniques, EDX pattern, to check the composition of the blank film and the doping film. Then we took some nice pictures by using SEM analysis. Then we put some suggestions for like suggested mechanism of the photostabilization for polystyrene with the new synthesized shift bases. Then conclusion. Okay, so actually the synthesis of polystyrene is just a simple reaction between this functional group, aldehyde, and the amine. Okay, then we made this, okay, this group. Okay, and here we have pictures just for the films. After we make film for the polystyrene, after it's doping with the photostabilizers, the shift base, and I've just taken pictures to share it with you. Okay, and here this is the FTIR spectrum. Actually, I did the FTIR spectrum for the synthesized compound, which is compound 3, the shift base. And I found all the important peaks which I needed to characterize my compound. So here in this study, again, we use the FTIR technique. So if you look to this blue line, blue curve, this is the blank polystyrene. PS is a polystyrene. Okay, and this is the blank polystyrene. And here, polystyrene doping with the shift base, with the stabilizer. Okay, and in y-axis, what we have the index for C double bond O, and this actually mark for the oxidation. Okay, so when we irradiate the polystyrene with UV light, here irradiation time, okay, and as we see from 0 irradiation time up to 300 hours, okay, and we monitor the, so what we did, we take two films, one blank film and the other one film doping with the shift base, with the stabilizers, and we put them exactly in the same conditions under UV. And each time what we do two tests for them. Actually, first we weigh them to see the weight. Is it decreased? Is it the same? What's happened for it? Okay, and the other thing, we take IR for it. We take it for the IR machine and measure it. And what we notice in the blank IR, the oxidation is higher. And this is actually the mark for the degradation. And we saw some stability, polystyrene with the shift base, okay? And the same thing, we notice it with the weight loss. This is the weight loss. We notice that the blank weight loss is much higher than the polystyrene with the shift base stabilizer. And this is actually clear evidence that our stabilizers is work to reduce the photo degradation of the polystyrene. As well, we did energy dispersive X-ray spectroscopy to see the composition of the compound. So this is for the blank compound, and the structure for a blank compound, the major element in the blank compound is the carbon, as we see here. While when we take it for the polystyrene and the shift base with it, we saw other elements like sulfur, oxygen, nitrogen, and it's just evidence that the stabilizers is like separate homogeneously with the polystyrene. We take some scanning electrons microscopies to see the morphological surface of the polystyrene. And as we see here, like this is the polystyrene before irradiation, a blank polystyrene, and this is the polystyrene after irradiation, and we can see clear like there is a damage, okay, within the surface morphology after irradiation, and that's normal, as we know. Okay, however, when we use the stabilizers, still there is a damage, but anyway, it is less than what we saw it in the blank PVC polystyrene. Sorry, and here it's 4 pictures, and it is actually the same picture, but just zoom it more. Okay, for all of them. So we suggested a mechanism how the shift vase or this stabilizers is work to stabilize the polystyrene. So let's imagine we have two molecules of polystyrene and we irradiate it with UV light. What we expect to see two free radicals here, okay? And the stabilizer, how the stabilizer work actually, when we have a free radical, and actually this bond is easy to break, this shift base bond is easy to break. So it could be break, okay, and link the polystyrene in one side. Like when we make a doping, it is just physical attraction. But now in mechanism, we thought that there is like chemical reaction, okay, like the polystyrene linked by covalent bond to the stabilizers, okay. And here still we have free radical. Then another molecule, free radical of polystyrene comes and link there. Then the result we have a stable compound, okay, with the stabilizers and two molecules of polystyrene. Okay, so that's the way how we think like our photostabilizer is work. We made as well like a graphical abstract, like we have the polystyrene, then this is the stabilizers, okay, and when the polystyrene with the stabilizers and we irradiate it with UV light, so nothing will happen to the polystyrene, stay the same, and just we will get out the UV light by harmless heat, okay. Conclusion, synthesize a new shift base and used it as photostabilizer for polystyrene. We have used different approach to measure the effect of synthesized stabilizers in reducing the photodegradation of polystyrene films under UV exposure. And finally, the result exhibited a significant performance for stabilizers in reducing the weight loss of the polymer upon irradiation in comparison to a blank polystyrene films. And finally, I would like to thank all of you for listening, and as well I would like to thank Al Nahrain University because all that work have done at Al Nahrain University Chemistry Department. Thank you. I'm ready if you have any question.
Time and your presentation.
Thank you.
Anyone have any question, please? Okay, Doctor, can I ask you?
Okay.
When you applied UV source and heat source,
yes,
you can use another source. It give us same work, UV and heat, like UV laser give us UV light and
okay.
high power, then give us high heat.
Okay. Actually, that's a good question. So to be honest, why did we use UV light? Because the PVC and polystyrene, it's used like outdoor applications. And this will affect by sun, and we know sun it has UV light. Okay, so the main aim to reduce the harm from the UV light. Okay, and and actually, if you look at the structure of my stabilizers, it has a lot of aromatic rings. Okay, and actually, all this conjugation system. If anyone chemist, definitely they will know that. This will absorb at the UV region. Okay, so this compound will absorb at the UV region, and it's like specific for the UV region. And actually, we don't need to use laser because we wanted to study how this material will affect by UV light. Yeah, that's the main aim. I hope I answered the question. Yeah.
Okay, thank you very much.
Okay.
Thank you for your
No
presentation. Anyone have any question, please? Okay, Victor, thank you very much for
Okay,
your
thank you so much.
presentation
Thank
and
you.
your
Thanks.
time.
Thanks
Thank
again.
you.
Thank you.
Thank you.
Bye.
We turn now to the sixth presentation, Dr. Mustafa Yunus, Abdul Fattah, oral, yes, oral, Federal University, Mira Street, from Russia. The presentation title, Development of Alpha Track Measurement of the Thermal Oven as an etching technique for SSN TDS.
Welcome everybody. Are you hearing me?
Yes, Mr. Mustafa, you can recognize yourself and start your
Presentation is clear. You can
Thank
see.
you. Yes, yes, it's clear.
Yes. Hello everyone. Today our presentation was titled Development of Alpha Tracks Measurement with Thermal Oven as an Etching Technique for Solid-State Nuclear Track Detectors. This is a cooperation between Oral Federal University in Russia and Mustansiriya University in Iraq and Mina University in Egypt and other collaborators. The aim of the present work, firstly, to study the effect of oven heating on the accelerate and the development of alpha tracks, as example from radium 226 source as alpha source, in two types of solid-state nuclear track detectors, CR39 and LR115. As we can see, the two types of detector in the two pictures. Then the used oven heating technique is compared also with the water pass technique. It's a traditional etching technique for the two detectors. Solid-state nuclear track detectors have wide applications like in the measurement of radioactivity and detect the radiation from alpha and neutrons, as we can see in these photos. In our work, we use CR39 detector with thickness 500 micrometer and no area for each detector 1 by 1 centimeter. This detector is developed and produced by a UK company. Also for LR detector, we used 1 by 1 centimeter sheet detector with thickness 112, and it's a developed by France company. The two detectors in our work are exposed directly to radium 226 source with activity 5 micro curie with as alpha emitter, and the pieces of detector exposed for 5 seconds, 10 seconds, and 15 seconds respectively. Then after exposure, we have etching, chemical etching. The chemical etching process is achieved using a chemical etching solution, sodium hydroxide, with a normality 6.25 at 70 degrees for CR detector and 2.5 at 60 degrees for LR detector. Then we can detect the tracks at the etch filter using optical microscope as shown. The parameter of etching, we can state that rho, it's the average number, it's a track density, average number of total tracks divided by area field view. VB, it's a bulk etching rate. D is the mean diameter. VT is the track etching rate. And VD is the diameter rate of the tracks. V is the etching rate ratio. And the last one is the etching efficiency. These parameters for the two detectors using oven technique as a heater are listed in these two tables. For results, here we can see the CR detector in the left side, tracks plotted with time of etching for the three exposure time, 5, 10, and 15 seconds. As we can see, the highest track density reached nearly at 90 minutes. If we compared with the right side for water pass technique, traditional method. Oven technique reduced the time of etching from 120 to 90 minutes. So it's improved and developed. Also, we can observe that the track density in each exposure time increase more than in water pass, and increase also with the time of exposure. The same we can observe for LR detector. With exposure time, the track density increase compared to also water pass technique. Also, we can observe that the maximum etching rate was at 40 minutes compared to 50 minutes in the traditional water pass technique. Here we can see in this figure the optical microscope photos from 15 minutes, 90 minutes, and 180 minutes, and 230 minutes. As we can observe, first it's difficult to count, and then at 90 minutes it's more precise to count, and after that at 180 there is some interference between the tracks. It's difficult to count, and also in 240 minutes. So as we mentioned above from the results, that 90 minutes it's a more accurate for track density. Also for LR detector, we can find for 15 minutes, 40 minutes, 60 minutes, and 80 minutes. As you can see, also 40 minutes is the best one. Compared to 80 and 60 minutes, we can see some interference for track. It cannot be counted. We can also reduce the diameter of tracks. It's a very important parameter for determining the activity and the properties of detector. Diameter of track for each exposure time is plotted with time of etching, and linear correlation is founded with fitting parameter for CR detector and for LR detector. Finally, we can reach to the conclusions. The results indicate that the increase of the exposure time doesn't have effect on the optimum etching time of the detector, but increase the track density due to increase the alpha flux reached to the detector with time. Secondly, the optimum etching time for the two detector with thermal oven technique is reduced compared to the traditional technique, like water pass. The optimum etching time of CR39 detector is 90 minutes for 3 exposure time, 5, 10, and 15 seconds with thermal oven, compared to 120 for water pass. For LR, 40 minutes for oven technique compared to 15 minutes for water pass technique. The track density or track diameter is increased directly with the etching time and with the radiation dose exposure time for the two detectors. Thank you, and welcome for your questions.
Thank you, Mr. Mustafa, for your presentation and for your time and control. Anyone of our audience have any question for Mr. Mustafa? Okay, Mr. Mustafa, can I ask you?
Yes.
When I think you used NaOH for as a solution, etching solution. You can use another etching solution like an HF or an HF with NaOH.
No, it's sodium hydroxide is used in this method as a chemical etching solution to detect the tracks of the detectors. No other solutions used.
Okay. Thank you very much. Thank you very much for your time and your presentation.
Thank you.
We turn now to the 7th presentation. Mrs. Hiyam Nazmi Badr, oral, Federal University, Mira Street, from Russia, and presentation title, outdoor aerosol characterization in two places, urban and oral measurements. Yes, Mrs. Hiam, please. You can recognize yourself and present your work.
Yes, I'm here. Just a minute, please.
Thank you. Thank you. You can present now.
Yes, sure. Yeah.